The Young's double slit experiment. Here, let's get some notes. So 1803 is when he's publishing his work on this. Had been working on this for quite some bit of time up to it, but there you go. So let's hit the major points. Even before we get to it, the specifics, let's remember that prior to this, we had a question. The question is, what is light? And so there were two main ideas. There was light that was a particle. That was the Newtonian idea of what light is. And then light is a wave. And that was a scientist whose name was Huygens, Hans Christian Huygens. And they both posited their ideas about light in the late 1600s. So this question is literally raging for quite some time before it was decided. Young comes up with a simple hypothesis. If light is a wave, it should display the property of interference. Remember, only two things that are waves can interfere, because interference means two things being at the same spot at the same time, and nothing with matter can do that. That's what the idea was. Only waves could do that. So if light can interfere, it is a wave. So how did he do this? Now, I'm going to do a slightly more modern take on this because we're going to talk about using lasers. Obviously, Young did not have a laser in 1803. He used prisms and lenses in order to refine white light down to individual colors. Totally brilliant. Brilliant, brilliant, brilliant. But it starts with the double slit. Now, I'm going to exaggerate the drawing. This drawing is not anywhere near to scale. And we'll talk about what's wrong with the scale in a couple of minutes. So here we have our double slit. So this is like a film. What Young did was he took a piece of glass, painted it black, and then with a knife or with a razor, he cut two slits into it. And it was very difficult to do it, to get those slits really close together. So we're going to call the separation between adjacent slits D. Because remember, I had a device that didn't have just two slits, but had a lot of different slits. We'll write down some stuff about that later. Then he had incident light. I was using red light, so here we go. I'll just draw it as a wave because why not? That has a specific wavelength, okay? Lambda, so another distance that becomes important. Drawing not to scale, lambda is tiny. The wavelength of light, red light, is like 650 nanometers to 700 nanometers, very small. The specific laser light that I'm using has a very specific frequency in a vacuum. Of course, we're doing this all in vacuum, that's 686.4 nanometers. So, we're going to use monochromatic light. Now, laser light is coherent, remember, so not only is it monochromatic, but it's in phase, so it's really bright and really intense, which super helps with this experiment. Then I'm going to have a screen over here. All right, so that's a screen. We're going to call the distance between our slits, which were on this film, and our screen L, right? Slit to screen distance. All right, and so what I'm going to do now is I'm going to put a dotted line that comes from directly in between the slits, because what did we observe over here when we did the Young double slit experiment? Well, remember, if light was going to be a particle, we would expect just a dot here and a dot here, the particles bombarding and just all going to the spots directly across from them. But what do we see instead? Well, we see a central bright dot here, and I'm going to do the size of the dot as proportional to its intensity, just so we could see it. Then we saw nothing, and then we saw another dot, but it wasn't intense. Then nothing, and another dot, and nothing, and another dot. Now, when I did it at home, we only saw that first dot here. We didn't see the ones up here because of the particular slide that I brought. Now, down here, what we saw was something that was equally as bright and symmetrically spaced. Boom and boom. And we'll call the distance between successive dots X. Okay? And so I'll just label all of these X, and these should be equally spaced under a certain condition. We'll talk about that condition a little bit later. right? So that was what we saw. So what does this prove? The fact that we saw places with light and places without light is sufficient to say that that light behaves like a wave because we're seeing constructive and destructive interference. The fact that there are bright fringes and dark fringes is sufficient. But we're going to dig down a little bit more and write some things more about this pattern, right? So in words, what's true about the pattern? So first is that there is a central bright dot or fringe is usually the way it's called historically. We now know that this is the central maximum or the principal antinode, however you want to call it, because that's going to connect to what we talked about. 2, that the pattern spreads out perpendicular to the slit orientation. Right? If my slits are vertical, the pattern spreads out horizontally. 3, that the pattern is symmetrical about the central antinode. Okay? 4, that each successive maxima gets less intense. We'll do some stuff with that in a little bit. And then maxima close to the principal max are equally spaced. And that spacing was X. And we'll talk to close to what that means and what that approximation is about. All right, cool. And then in the video that I did, we saw some proportionalities. We saw that X, when the spacing between the maxima, or the spacing between the slits got smaller, X got a lot larger. That was the difference between his experiment on the video and my experiment. On my experiment, the separation distance D was really, really small. Therefore, the X's were really, really big. So 1 over D, where D is defined to be the average slit spacing. And while I'm here, let's just talk about the device that I had. It was called a diffraction grating. And the particular diffraction grating that I had 700 lines or slits per millimeter, which is ridiculous. That means that the D for this particular diffraction grating is going to be 1 over 700 millimeters, which is really, 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 really tiny. The other thing we saw is that if I moved the slits closer to the screen, that X got smaller. And that should make sense because we saw how those antinodal lines were fanning out. And if I just intercepted those lines sooner, coordinate geometry would just tell me that X would be smaller. So X is directly proportional to L. Remember, we're getting all of this empirically. I haven't proven anything, but it's empirically true. And then we saw, I did the experiment with green light and red light, and we showed that with green light, the maxima ended up closer in. Therefore, as the wavelength got smaller, so did X, right? So violet would even be closer. We saw that violet was always closer in. So that's another direct relationship there. And so if we put all of these together, we can see that X is equal to lambda L over D. We're going to box that equation. That's our empirical equation. We will get we'll derive that in a different way in just a minute. But this is going to be the equation we're going to use. So that is what's going on. That's how we can find out what X is. So knowledge of the pattern, knowing that these are equal, if I wanted to know where the third order maximum is compared to the central maximum, that would be a distance of 1, 2, 3. That's the third order max. Actually, let's label them. This is the principal maximum or the central maximum. So the principal. This is the first order max. This is the second order max. This is the third order max. And same thing down here. Well, if we have maximums, notice I'm drawing these as very distinct dots. Well, in the experiment that we saw online, though, it was more like they were blurs, and there were places where there was bright intensity, and then there were places where it dimmed out. There is one and only one spot where this goes all the way to 0, and that's going to be here at the first order min. Where do you think the first order min is? Well, hopefully you said at half x, because that's the pattern that we talked about before, right? So here, directly in between those, is where the mins are. So here's the second order min, third order min. So if I want to know where a minimum is, I can just count it out from the principle. So where's the third order min? It's at 1x, 2x, and another half, so 2.5x. So there you go, that's the way. So that's our knowledge of the pattern. That's how this is the equation we're gonna use to solve problems. But still, why is all this happening the way it is? Well, we have to go back to what we talked about before, right? Why were we getting interference, the interferences that we were getting, where we were getting them? And it's the same reason as we saw when we did two-dimensional interference patterns before. So why does the central maximum occur here? Well, the reason is, if I consider each of these slits to be a source, source 1, source 2, and I talk about the light traveling from source 1 to that point and source 2 to that point, boom. Those two distances are equal, and that means that the waves arrive in phase. Remember, that's because the path difference here is 0 lambda. Oh, so if this is the first order max, what do you think is true about from source 1 to the first order max and source 2 to the first order max? Oh, here the path difference is equal to exactly 1 wavelength, that this path is exactly 1 wavelength longer than this path, so the waves arrive in phase. That's the first order max. At here, the first order min, the path difference is equal to half lambda, and so on and so forth. But that's really nice because that correlates pretty clearly with something that we said here. Notice here, the first order max is happening at x, or 1x. The second order max is happening at 2x. The third order max is happening at 3x. Well, what's the path difference to the third order max? Oh, that's 3 lambda. What's the path difference to the second order max? Oh, 2 lambda. So this number correlates also with the path difference. How about this? Oh, the path difference to the first order min was half lambda. The path difference to the third order max was 3/2 lambda. But notice it's also 3/2 x up. So if I know the knowledge of the pattern, that correlates with the path difference. And that gets us into explaining exactly what's going on here. So I want to draw another picture, and we're going to try and derive that equation in a different way. And it's a bit of a mind trip. So buckle up. Here we go. Normally we'd spend like 2 days in class on this. I'm going to kind of just walk you through it. So here we go. That distance there is L. Let's say that this is the first order max. That means this distance here is x. I'm going to put then a line out there. That's what that antinodal line looks like. And we're going to call this theta. Theta is defined as the angle of diffraction. It defines how far out that wave is bending, right? So there we go. Now, at the same point, what I'm going to do here is I'm going to create another triangle. Okay, so that is D. Now we know, boom and boom, that let's call this point A. Yeah, we'll call this B and this is C. So the distance from B to C is D. We also know that A to B and A to C have a relationship. The distance from A to C, or C to A, is equal to the distance from B to A plus 1 wavelength. That's the definition of where this is. By the way, this derivation I'm doing, you don't need to know it. You don't need to know it. I just feel I need to show it to you. Okay? So this is exactly 1 wavelength longer than that. So there must be a spot here, I'll call this, I don't know, point D, such that AC is equal to B, or actually AC, oh, hold on, I screwed up. Yeah, AC is equal to AD plus DC, right? So if we look here, AD, let's say that that is the same as AB. That would mean that DC is equal to 1 wavelength. Now if you notice here then, I have another little triangle. And so let me pull that little triangle out. That triangle has lambda as this side, D as that side, okay? Now, it just so happens that this has the same angle as that diffraction angle. There's a similar triangle thing to do there. So here's where it comes down to, and this is sort of the weird thing. Let's think about this triangle. Talk to me about this triangle, BAD. Notice that I've made this a right triangle, right? So that's a right triangle, and this is a right triangle, right? AB is equal to AD. And people are like, hold on a second. No, that can't happen because that would mean that ABD is isosceles and the base angles would both be 90. You can't have a triangle whose base angles are 90. And my answer is you can. All right, so hopefully you have said I'm insane and that's no good. And I'm gonna get back to all the approximation stuff that we've been talking about. I told you this picture is wildly out of scale. This is where this comes in, right? Look at this. L, when I was doing this in my bedroom, was like a meter. X was like half a meter. D was fractions of millimeters. Lambda, which is this distance here, is nanometers. This triangle is on such a different scale as this triangle. If I wanted this triangle to be scaled, I would need to have this over in 4 apartments away from me in order to get it anywhere near to scale. Meaning that this angle here is actually really small. Really small because of the scale of this, right? So imagine if this angle, because this spot would be really so far away, that these two lines are the same length, and that's so small compared to this, that this angle is probably like 0.000000004, right? Like some really insanely small angle, such that these lengths are virtually the same. These would not be 90, but it's like as those angles approach 90, meaning L must be much larger than D for all of this to work, okay? That's what I'm talking about. L has to be much larger than D for all of what I'm about to do to work. So let's look at the triangles. That works. L is much larger than D as long as we set up our triangles, or rather our physical apparatus right. So here's L, here's X, and I said that's theta, and that side triangle, I had lambda, D, and theta. So if you notice here, I've got tangent of theta is equal to X over L, and I've got here sine of theta is equal to lambda over D. That's super interesting because let's come back to that empirical equation I derived. X was equal to lambda L over D. Let's just rearrange that. X over L equals lambda over D. Going back here, ooh, X over L, lambda over D. Oh, damn it, they're not equal to each other because X over L is equal to tangent of theta and lambda over D is equal to sine of theta. Darn it. Oh, okay. Well, here's the thing. Grab your calculator. What I want you to do here is let's look at sine of theta and tangent of theta. And let's look at 1 degree, 5 degrees, 10 degrees, 15 degrees, 20 degrees. If we put that into our calculator, and we do sine of 1, you get 0.01745. So there you go. How about tangent of 1? Put that in. Oh, I got 0.017, well, this is 45. 4, 5. Oh, it's equal. Interesting. Sine of theta. Sine of 5, 0.187. We'll go one more. 2. Tangent of 5 degrees. 0.087. Oh, this one's different at the 10,000th place by a little bit. Sine of 10 degrees. Okay, sine of 10, 0.1736. Tangent of 10, 0.1763. Oh, so this is off at the thousandths place by a little bit. Sine of 15, 0.2588. Tangent of 15, 0.2679. Oh, so this is off at the 10th place now, but actually slightly less than the 10th place, right? Meaning that these are still within 1% of each other. Sine of 20, 0.3420, and then tangent of 20, 0.3639. Okay, that's off by more than by more than 1%. So there's somewhere in here between 15 and 20 where the sine and tangent deviate by more than 1%. So in other words here, folks, as long as we keep theta really small, this is a true what's called functional equation. And when we do these experiments, if I can't keep theta small, I just use these two in conjunction with each other. Now, in everything that we're going to do, we're going to keep them equal. We're going to keep the angle. We're going to assume we're doing what's called the small angle approximation. Small angle approximation, and in this case, the sine of theta is the same thing as the tangent of theta, as long as theta is somewhat less than about 17 degrees. That's where it deviates by 1%. And so in this experiment, you can see that. That's why when I went back here and I said that these x's, I said maxima close to the principal max are equally spaced. That's because close to the central maxima, that theta is going to be pretty small, so that we know they're equally spaced. Beyond that, they start spacing out a little bit more and more and more, but we're not going to care about that. So at the end of the day, this is an application of the two-dimensional interference pattern we talked about. This is going to be the equation that we're going to use in order to do our calculation work. And the last thing I want to say about this equation, notice that this equation is all physical distances. So it's really important when we do this problem that we make sure we have all of these in the same set of units. I would recommend converting everything to meters before doing the problems. And so with that, Young's double slit experiment, the math bears out exactly the same thing that we empirically derived. Notice our empirical derivation has a little bit of variance to it to reality, but enough to do the sort of work that we need to do.